Hello, everyone. I'm Pranav. I'm going into my fourth year as a graduate student at Caltech. And today I'm going to be talking about using NERC2 LGS to search for tertiaries to black hole and neutron star binaries. So when I say that, I specifically mean binaries in which a normal star is orbiting a neutron star or a stellar mass black hole. These systems are quite rare, and we're not entirely sure how they form. For the systems that we do know of, their current orbital separations are less than the predicted maximum radii of the red supergiant progenitors of the black holes and neutron stars, which suggests that the two components would have interacted in the past. And because the primary to secondary mass ratios are so large, we expect the resulting mass transfer to be unstable, leading to an episode of common envelope evolution. So this already represents a challenge to the standard isolated binary evolution formation model for these binaries, because we would expect some significant fraction of these binaries to merge. But let's say that the lower mass star is successfully able to eject the envelope of the red supergiant, then what we end up with is the star orbiting a helium star in a tight orbit. Then, presumably, the helium star goes supernova. And this represents another hurdle for this model, because the resulting mass loss, or natal kick, can just unbind the binary altogether. But let's say the binary survives this as well, and the resulting picture is generally the story that is used to explain the formation of close accreting neutron star or black hole binaries that, for example, are called low mass X-ray binaries. However, recently, using Gaia astrometry, we have started to discover non-accreting black holes and neutron stars in much wider AU scale binaries. So what I show here is a plot of compact object mass versus orbital period, and you can see that the so-called Gaia black holes and Gaia neutron stars discovered using this method fall in a completely different region of parameter space than the X-ray binaries and the pulsar binaries that we knew of previously. And clearly, the orbital periods that we observe for the Gaia black holes and Gaia neutron stars are in tension with the final orbital period distribution that is predicted by this model. And it's because of that the hierarchical triple evolution formation pathway for these binaries has become a lot more popular in recent years. So to give you an idea of what this story is, for black hole or neutron star low mass X-ray binaries, you can have the components initially form in a wider orbit and then have a distant tertiary induce Kozai-Lidov oscillations, which then together with tidal dissipation brings those components closer together at a later stage. Meanwhile, for Gaia black holes or neutron stars, those Kozai-Lidov oscillations can actually delay the onset of common envelope evolution, leading to wider separations than you would have expected otherwise if the binary was isolated. So, do we have any observational evidence that supports this theoretical pathway? Well, actually, yes. The low mass X-ray binary, well-known V4 for Cygni, has actually been shown recently to be part of a hierarchical triple. So I show here two images, one from the Digital Sky Survey and one from NERC2 of V4 for Cygni. And I've shown the location of that binary with a red circle. And you can see around 1.4 arc seconds to the north of the target, there is another star. And for many years, people thought, oh, this is just some kind of annoying interloper. It's a chance alignment. However, using Gaia astrometry and follow-up RVs, it was shown that the proper motions of that star are actually consistent with that of V4 for Cygni, and its RV is consistent with the systemic RV of that system. And so therefore, it's actually a weakly gravitationally bound tertiary and not a chance alignment. So why does this motivate us to look for such tertiary companions to other black hole or neutron star binaries? Well, it just turns out that V4 for Cygni is nearer and brighter than most black hole LMXBs. If the system were 50% more distant, that tertiary would have been blended with the inner binary, and Gaia would not have been able to resolve it. If the tertiary were 10% more massive, that tertiary would have already evolved into a white dwarf that would have been below Gaia's detection limit. And yet, if it was 20% less massive, it would have been too faint for that precise proper motion analysis. And so this suggests that harder to detect tertiaries may be hiding around other binaries, and we just need to go deeper and have better spatial resolution to find them. And that's where NERC2 LGS comes in. So we proposed and received 3.5 nights on NERC2, and we had goals that were threefold. First, we wanted to find companions that were too faint to be detected in survey imaging. Two, we wanted to detect companions that were unresolved in survey imaging. And if we did find any promising tertiary companions, we wanted to compare our images against any archival images of X-ray binaries that existed already in the archive and measure proper motions over a long time baseline to determine if those companions were indeed gravitationally bound. To just give you an idea of what we were trying to do, here's both a pan-stars image and one of our follow-up NERC2 images of a black hole X-ray binary called Swift J1727. I've marked the location of that binary with a purple circle in both images. But what I really want to draw your attention to is this source that is to the northeast of the system, which I've marked with a red circle. It basically looks like a blob in the optical pan-stars image, but in our K-band NERC2 image, you can see that it is resolved cleanly into 3 different sources that we didn't know of before. Now, we can't rule out that any of these are tertiaries, but yeah, they're around 2.5 arc seconds away from the source, so it's more likely that they are chance alignments. But this is just to show you what the power of NERC2 really is. So what were the results of our survey? We looked at 5 quiescent black hole low mass X-ray binaries other than V44 Cygni, Gaia Black Hole 1, which is the closest black hole system to Earth, and 12 Gaia neutron stars. But in the end, unfortunately, we did not end up detecting any promising tertiaries that were undetected or unresolved in survey imaging. Okay, does the presentation stop here? Well, no. What we can do is place some quantitative constraints on what tertiaries could still exist. So let me just take Gaia Black Hole 1 as a typical example. Here's a reduced and stacked image of the system. You can see that the AO subtraction is not perfect and there's some speckle noise. So what we do is create a contrast curve, which tells you what is the faintest source that we could detect as a function of angular separation. And you can see that at separations greater than around 1 arc second, we can detect anything brighter than a K-band magnitude of around 22. And using that, we can place stringent constraints on potential main sequence tertiaries. We can rule out pretty much any solar mass tertiary and any tertiary above the hydrogen burning limit at separations greater than about 100 AU. We're only able to place weaker constraints on white dwarf tertiaries, which are fainter potentially. But again, at separations greater than around 500 AU or so, we can rule out any plausible white dwarf tertiary. For the specific case of Gaia Black Hole 1, in an earlier paper, I reported some precision RV measurements that we collected for the system with Espresso. So even if there was a tertiary that was closer in that we didn't detect with NERC2, it could potentially induce radial velocity perturbations to the spectroscopic orbit of the luminous star in that binary, which we would have been able to detect with the Espresso measurements. So in combining our AO imaging, the RVs, and spectral disentangling, we're able to rule out a large region of allowed parameter space for a potential tertiary in Gaia Black Hole 1. Of course, we don't rule out everything. Might still be a chance, but what I can tell you is that Gaia Black Hole 1 is indeed unlikely to be a hierarchical triple. So I'm not going to show you the contrast curves of every single system that we observed in the interest of time, but the main takeaway is that at separations greater than around 100 AU, the contrast curves that we created ruled out pretty much all plausible main sequence tertiaries to that system and any young and hot white dwarf tertiaries. But fans of the hierarchical triples need not despair because there could still be cool white dwarf tertiaries that we were unable to detect. Okay, in the remaining time that I have left, I want to talk about something just a little different. It's an interesting millisecond pulsar binary recently discovered by Yang et al. In 2025. They showed that millisecond pulsar is in a 3.6-hour compact binary and that has a companion between 1 and 1.6 solar masses. What's interesting about this binary that is different from other systems that would be otherwise similar is that if you look at the radial light curve, which I've shown here, there is eclipses over around 17% of the orbit. However, the companion to the millisecond pulsar is undetected at all other wavelengths. And so by summing all of this information together, the authors proposed that the companion is a stripped star. We wanted to follow this up with NERC2 to test that hypothesis. So we got a bunch of images over one orbital period, and we stacked them. And what did we find? First, let me show you some survey images. Here's the pan-stars field in the optical. There's so much extinction that you see nothing at the location of the pulsar. UCURT in the near-infrared does better, and our NERC2 image, which is shown as a cutout, is even better than that. But what I've shown there in the small red circle is the radial localization of the millisecond pulsar. Lo and behold, you see nothing there. So we can place a phi sigma detection limit of a K-band magnitude of 21.3 at that radial localization on any potential strip star companion. So what does that mean physically? Well, using some plausible dust map, and models of strip stars that are available in the literature, you can predict what the apparent K-band magnitude of a helium star would be as a function of distance. And what you see in the left panel here is that for any plausible helium star, even in the most pessimistic case, we can rule it out using our detection limit. So that hypothesis fails. What else could the companion be? Well, it could be a massive hot young white dwarf that would have evaded our detection. But how could that explain the observed eclipses in the radial light curve? Could it be due to some kind of wind from the white dwarf? Perhaps some interaction with some material that was ejected from the common envelope event? In any case, I'll leave that as a mystery for you to ponder while I throw out my conclusions here that you can peruse. Thank you for listening.
So